So for question 5a, we're told to justify the stark difference in acidity of the following two compounds. Provide the mechanism for the acid-base reaction that occurs with water for one of them. So what we need to do here is recognize that we have two protonated amines, and they're decent acids. This is quite a good acid with a pK of zero point 0.4, very low pKa, is very close to being a strong acid. That is something that would completely dissociate in water. Uh, the other amine, secondary amine that's in its protonated form, has a pK of 11.3. So it's really a fairly weak acid. Why is there such a difference between these two? Well, one of the clues that should help us, it says provide the mechanism for the acid-base reaction that occurs for water with one of them. And in fact, I'm really just trying to get you to think about the acid-base reaction. I would take a look at the acid-base reaction for each of them. And there we go. Let's put it here. And let's push the arrows for one of them. The arrow pushing is going to be the same for both reactions, so we won't be too concerned. And what happens in an acid-base reaction with water? Well, if this is the acid, water has to act as the base. And we see we're losing one of the protons from this nitrogen, and it's landing on water to form the hydronium ion. So let's go ahead and push the arrows here. The arrow pushing, as I mentioned, would be the same for both of them. Lone pair of electrons from the oxygen is going to reorganize to pull off one of the protons on the amine and form our hydronium cation and our conjugate base. So this is our conjugate base, this is our conjugate acid. The mechanism would be the same for this reaction below. Let's go ahead and put that in. You didn't have to do this, you weren't asked to do this, and I'm doing it slightly different. There we go. Same thing happens. Water is the base, pulls off a proton, gives us our conjugate acid and base. The conjugate acid in each case is the same. It's H3O plus. So all we have to look at is the difference in the stabilities of the conjugate base. And hopefully we're struck by the fact that this thing has a number of sp2 hybridized carbons, and the nitrogen in this case, we might think of it as being sp3, but it actually gains a lot of energy by rehybridizing to an sp2 hybridized nitrogen and leaving this lone pair of electrons in a p orbital that can then conjugate with the rest of the molecule, and we then get an aromatic system. We have two electrons in each of these pi systems, and then if we conjugate the nitrogen electrons with that by rehybridization and allowing that lone pair of electrons to be in a p orbital, it conjugates as well. We have 6 electrons in a planar cyclic conjugated system, thus it's aromatic, a very stable situation. So we get quite a gain in stabilization of the conjugate base by deprotonating it. This thing is non-aromatic, this is aromatic, so we get a considerable energy gain through the aromaticity. In the case of the secondary amine below, it's non-aromatic. All of the atoms, the carbon atoms and the nitrogen, are sp3 hybridized. And in this case, there's no gain in stabilization for the nitrogen to rehybridize and become sp2 hybridized, because we can't conjugate that lone pair of electrons with any pi system, because all of these other atoms are sp3 hybridized. So there we go. The reason for this is the gain in energy, because we go from a non-aromatic system to an aromatic system upon deprotonation by water. So here we go. We need to explain this to the person doing the marking. So let's do that in words. There we go. So question B is kind of similar. It's telling us that chlorocyclopentane undergoes a slow hydrolysis reaction while 3-chlorocyclopentane cyclopentene hydrolyzes very rapidly. I've given you the structures. You should be able to figure out by the names that this is chlorocyclopentane, this is 3-chlorocyclopentene, And this is 5-chloro-1,3-cyclopentadiene. And in this case, there's no reaction. So what's going on here? I've said explain. I've told you it's an SN1 reaction. So we have to take a look at how an SN1 reaction undergoes. And we don't have to draw a whole lot. We know in SN1 reaction what happens is we will lose chloride in the first step for each of them. And I'm just going to do this. I'm just going to copy that because the mechanism is the same in each of them. And what does this arrow pushing indicate? That this pair of electrons in the carbon-chlorine bond is are leaving to break that carbon-chlorine bond. The electrons are going with the chlorine, so we're going to end up with a chloride anion and a carbocation. Let's take a look at those carbocations. All of them then have to undergo a reaction where there's an intermediate. I'm going to put a little box around this just to keep it separate. We didn't write out the whole mechanism, but again, we kind of did, just not in our traditional fashion. I'm showing you that these dissociate. These are the intermediates. They collapse, then with water attacking, followed by deprotonation to form our products. In this case, we have a secondary carbocation. We know secondary carbocations are more stable than primary, less stable than tertiary, but also less stable than allylic. So in the second reaction, we have an allylic cation form. Notice that positive charge is conjugated with this pi system. So we can draw resonance structures where we have carbon-carbon double bond here and the positive charge in this position. In the case of the cyclopentadiene, we have the cyclopentadienyl cation, which sp2 hybridized. All of the carbon atoms are sp2 hybridized. We only have 1, 2, 3, 4 electrons in this system, so it's anti-aromatic. It's going to be very stable, and hence it won't form. This is more stable than either of them, actually. And the secondary carbocation, we know that we can get reactions from that. So again, let's go ahead and put this down in words. There we go. And that answers those questions.